Yeah. Start then.
It started. Okay.
Yeah. Started. Sure. Yeah. So first problem is our equal rational numbers. So we are given these two strings s and t, and each of them represents a non-negative rational number. We have to return true if and only if they represent the same number. The string may use parentheses to denote the repeating part. And they have given the definition of rational number that it can be divided into up to three parts: integer part, non-repeating part, and a repeating part. And it will be represented in these three ways. This is like integer part. This is non-repeating. I mean, it's ending, but these are recurring. Like 9 will occur 0.9999 times, right?
What's that?
Same way.
0.99. Okay.
Yeah. So the repeating portion of decimal expansion is conventionally denoted within a pair of round brackets. Yeah. Like this 6 is repeating, 1 is repeating 6 times. That is what. So these two numbers are actually same if you see, because 0.52 within a bracket it is, so it will repeat this many times, and this your 5 is repeating 25 such times, so they are same
Mhm.
after 25. And this is also same. I mean, if you expand it,
Mhm. Yeah.
and
So the last example, example 3, actually is slightly different, right? So it says the first S is point 0.9 and then bracket 9, right?
yeah,
T is just 1 point.
so
So,
that
yeah.
yeah, 1 point represent. So this should, why true it is? Oh, is it approximating or what? They have
Uh,
given some.
because 0.9999 actually will represent 1, right?
Yeah, approximating, right?
Uh, that is what the double representation is usually, because if it is 1.0, then within one digit at the very end, maybe the 20th or 30th digit, you know. So if it changes by 1, it will be converted to 1 point instead of 0.999, right?
Oh, yeah.
Yeah, so therefore it is same.
Yeah, this is little bit different. It is, yeah.
Yeah, so that actually is the main, I think, because I was initially, when I looked at the problem, I started thinking, okay, so if I look at the example one, I said, okay, let me actually convert both of them into similar strings, right?
Mm.
And then truncate them at a certain length, okay, maybe say 10 or 15, something like that, and then compare the strings. That should work. But this last example actually is totally different, so you can't do that, right?
In this case, yeah.
Yeah.
Or one way, like you convert them to fraction and then compare.
Okay, so okay, that was a very good one. Like you say, you convert to fraction. So do you mean to say like you convert as a numerator, denominator, and all that stuff
Yeah,
like that?
that is what is like this one, this way. I mean, if this is given, you
Uh-huh.
convert to this format.
Okay, but then how do we do that? Especially for 1 and 0.999. Hmm. Yeah.
In Python, we have fraction. What do you say? This
Uh-huh, really? Uh-huh.
area.
So you pass this input and then it converts to fraction?
Yeah, but
Okay.
internally, I'm not sure what they might be doing. I think,
But still, do you not have to extract the portion from the non-repeatable, repeatable,
yeah,
and then
those pre-processing things you have to do, like
okay,
remove these brackets and all, decimal, all those things.
okay,
But
uh-huh.
once you get in a pure decimal format, you can pass it in a fraction API, and it will
Mhm.
fetch you the fraction.
Oh, okay. So in that case, that this can here also you can do, like in case of the example one, you see the bracket and 52, right? Sorry,
Okay. Oh,
example one. Yeah,
yeah,
okay. So if you look at the string t, 0 is the integer part, 0.5. If you look at 0.5, it's a non-repeating one. So 5 divided by 10, okay, that can be one of the fraction. And then you take 25 divided by 100, that can be another fraction, right? And then you form a GCD in that, like 25 and 100. And what is the GCD will be 25. You divide both of them by 25. So it'll be 1 by 4.
Yeah.
So maybe something that can be done. But then again, the thing is like, what for that 1 and 0.99? Oh, did you? Okay. Shashank, are you back?
Yeah. I'm audible now. Yeah.
Okay. So, okay, were you thrown out by the server?
Yeah. I
Oh,
was disconnected for some
okay, okay. Yeah, no problem. That happens for every one of us. Yeah. So that is what I was thinking, So then for the example three, it is 1 point and 0.999. So that actually you cannot convert into fractions, right? Maybe that is possible. I never thought about it, how it could be done. Because when you see 999, right? So even if you
Yeah.
start dividing them, they will be still approximates, right? Can they be exactly like because 1.0 is totally different than zero point 0.9 divided by 100, maybe 0.99 divided by 100, or something like 99, something like that, divided by 10,000 or so. I don't know. I'm
Yeah.
just thinking loud in that case, Yeah. So, so yeah. So, what is the approach that you,
Like some of the steps, like
whatever
I
you,
was, yeah. I think it was like this. Let's say this is your in a decimal point, right? After pre-processing, you'll obtain this, right? And you pass this into in your API. But if the things are like 0.1 into 5.2, so we are adding this away. What is it? 1 by 10 plus 52 by 990, right?
okay. So, why do you get 52 by 990?
Because this is your thousand. What do you say? Point. The 5.2 will fall in thousand range, right?
Mhm. So, therefore, you have to divide that by 990.
Nine, yeah.
Mhm.
Or I don't know. Internally it might be doing the infraction part.
No, I think what you are doing is correct, but I was not able to, correlate that stuff, you know. So therefore, I didn't, because that is a very good way of doing it, right? Actually creating the fractions, because then you are actually comparing the real numbers, correct?
Yeah. Hmm.
So in that case, the 1 point and 0.99, so that will also make sense if you do it this way. But I was trying to do that following someone, like this, the way they did 52 by 990. So I couldn't understand why it was 990 and not 52 by 1000.
Because they are. I don't know. I mean, okay. I think let's go through this. Maybe might come because I saw this one only as a what do you say? The
I think
bit simpler
what you are
constant.
doing is correct.
Yeah. Yeah.
I don't see any problem in that. It is the way we should do. But I was trying to understand how, because if you say 52 by 990, then actually if you really divide that, it will give you that value. So like
Yeah. So,
0.052. You know, so So that is the way you do such type of divisions, because it is after some decimal, right? So
yeah.
that many number of whatever that size, whatever you get prior to the repeatable one, that many number of zeros or that many number of raised to 10, power raised to 10, actually that number you have to subtract from the denominator of whatever you get for 52, right? 52 divided by 1000 instead of 52 divided by 1000, it should be 1000 minus 10, because 10 actually corresponds to zero point 0.1, right?
Yeah. Hmm.
So yeah, I was following
So
that, but
it
yeah, okay.
was. I mean, what they are doing is 10 raised to the power whatever the length of your repeat minus one, right? I mean, if it is an integer, so that's not a problem in that case, right?
Okay.
Mm, the way they are breaking. And that second part is like 10 raised to the power, whatever the length of repeat is, minus 1 into
Mhm.
again 10 raised to the power non-repeated decimal. What we are breaking.
Yeah, so if you look at the first one,
Yeah.
10 raised to the power of repeat. So repeat is 52. Okay.
Yeah.
So repeat size is 2. Okay.
2.
So 10 raised to
100 minus 199.
100 minus 199. Okay. Yeah. So that is
Into.
actually you're doing for the line 22, right? Yeah.
Yeah.
And then you multiply that by 10 raised to the power of
Non-repeat decimal.
non-repeating decimal, which is 0. So it will be 1 in that case, correct?
Yeah.
So that is the repeat fraction, which will be 99 in this case, right?
99. Yeah.
Okay. And then you are actually dividing that somewhere else. Okay. Maybe numerator is somewhere else, correct?
Yeah. And then at last I'm just comparing those S and T.
Yeah.
Like first
So you'll have
passing
to do
my
that.
S. Yeah.
Mhm.
So if this, what do you say? If this bracket is not there, that means there is no repeating. All are integers only, right?
Mm-hmm.
So you directly pass that S into fraction and it will give you the fraction for that S. And if it is like these type of cases, the line 23, then for based on the bracket, I split into non-repeat and repeat. Repeat will be your within the brackets, right?
Mm-hmm.
That's why I'm removing the, what you say, the last bracket, because I don't need to include this part I'm removing.
Right. Mm-hmm.
So after removing it, again, whatever non-repeat part I got, non-repeat part is this one, right? That I'm splitting based on the points, decimal.
Okay. Mm-hmm.
Yeah. And then in repeat fraction, the integer of repeat part, and this is the same, what is it, 10 raised to the power length of repeat minus 1 into 10 raised to the power length of non-repeat.
Uh-huh.
And whatever repeat and non-repeat we got, just add them, like 1 by 10 plus 52 by 990.
Okay. So your fraction is a class, correct?
Yeah,
Okay. And then the first parameter that you are passing is the numerator and the second is the denominator, right?
denominator.
Okay. Okay.
Yeah.
So in
Yeah.
that case, you do the repeat. So in the numerator, you are just going to pass the repeat, right?
Yeah,
Okay.
because it will, an integer part you have to take for numerator, right?
Mm-hmm.
Yeah.
But in the case of 52, you still have 52 as a numerator. So how are you passing that?
In case of 52, right?
Oh, that is the
So
repeat, right? Okay, yeah. No, my bad there. Yeah. So
the
that is what
identity,
you're doing as a repeat. So that is what you're doing on line 14,
yeah,
right?
repeat part, yeah.
Uh-huh. And then you are
Because
also having a non-repeat. Uh-huh.
non-repeat part.
Repeat fraction you are adding to the line 16, you are adding to the non-repeat one, and then you are returning it together.
Then to the constant, and then
So
comparing line number 18.
okay, so when you add them, both of these numerator and denominator, they might be getting added in that uh, object, right?
Objective. So this is what I'm importing from fractions.
Oh, you have a fraction that is a class already defined.
Class. Yeah.
Mhm. Okay, so the non-repeat and then the repeat, yeah, because that is the way it should go, right? First the non-repeat and
And
then
then the,
repeat. You're calculating everything on the top. So for the non-repeat, you don't have to pass any of the denominator.
yeah, because yeah, because it's fixed, right?
Hmm. Okay, so from the decimal, you are just comparing that as a different one.
Yeah.
Okay, that's slightly difficult, right? Because
Yeah.
see, if you get an integer, okay, in the case if it is 1 point or 2 point, I'm not sure whether we have a 2 point, but if you have 1 point, so it is prior to the decimal. So that
1 point.
also becomes a part of non-repeat.
Mm, I didn't get come again.
So if it is 1 point something.
Okay.
Repeating, do we have like that 1 point? So if you have a number like 1.4, okay, yeah, 1.4, and then you have bracket 24, something like that. So is that a valid test case?
Let's run. I think it should be right because
I don't know because it depends on the constraints. So one might be the max in some cases. They are not saying that like that anywhere.
your invention example they haven't mentioned each part consists of only digits will not begin with two or more zeros. Okay, it can be right. It's a valid.
I don't know.
But how will you compare one more string we need to have for that? 1.4 to
Yeah,
4
even
something.
if it passes, that should be fine, right? Even the value is false, the result is false, it's okay.
It's a valid test case,
That's not
right?
important. Yeah, even if it's valid, that is fine.
Yeah,
It's
it's a
valid
valid one.
test case. Okay, yeah. So that is possible. Okay. So so you're already passing that non-repeat. In the non-repeat, you collect both of them, it seems, correct?
Yeah,
So integer part, you don't do any splitting. So that complete is passed as a non-repeat. So you only add this fraction. In the fraction, you just separate the numerator denominator for the ones which you are repeating.
the recurring part. Yeah,
Mm.
10 is not. Yeah.
So it might be internally doing that stuff, because you're adding it on line 16. So the non-repeat part in the case of 1.4, it will just pass that as 14 by 10, right? So
Hmm.
that might be stored in the object, and then when you are passing the repeat fraction, so whatever the numerator and denominator you are giving, that will be added to it.
To next.
Mm, yeah, makes sense. Hmm.
Which
But
again,
this,
it's not a simple way to do, right? And
yeah,
mm,
if you look at this way, what you are doing,
yeah, then
yes. So Nick has something to say. Yeah.
to prove 52 new use calculator, right?
Yeah, of course, I can use calculator, but if I will be asked how to prove it, yeah, yeah,
Yeah. That is also really important. Yeah, what you say makes sense. I was also thinking of how it can be. So you come up with this, and then suddenly someone asks you in an interview, "How did you think of this?" That then actually is a main challenge there. Yeah, I agree. But maybe there are some proofs on this, right? Now it is very evident, right? The way you are doing it, Shashank, it works,
Yeah.
correct? So, do you have any way? Did you think any way, Nick or Shashank? How it is like I'm also slightly because went the other way. I just what did I do is uh, you know, extracted all these things and then convert it into a double. Extracted
Okay.
the string, yeah, and then normalize the string to some extent. Okay, so then I followed that pattern, and then when you convert to double, so automatically the library function does the conversion, correct?
For this, yeah.
Yeah. So yeah, one is this way to do the way you have done, or the second way will be normalize the string in the sense like when you have a 0.52 and you have a repeat of 52, so you actually add 52 about like 16 times or 20 times, okay? And the same thing you do for the one on line 26 with 0.152, right? Then you say 1 and then you 52, or maybe it's not correct that way. I think it is 252, right? Something like that.
Yeah.
So yeah, then you keep on adding that for 16 or 20 times for both, and then you pass that to a library function, that string, which is like a stod, ASCII to decimal or ASCII to float or double values, right?
in that. Yeah.
Yeah, and then they will convert, and then you compare those two double numbers, right? So that will work, but I'm not sure whether that will be an acceptable way of doing it, you know. But if this is the way, then we'll have to understand why, as Nick also said, like 52 by 990, why it is that.
Converting.
It works fine, but why it is? It might be a very simple thing which we are missing, you know.
In your case, Santos, when you convert like 0.9999 and 1.0, and then you get a double, right? How do you conclude that they are equal?
Yes. It was
Well,
share.
actually, what happens, the the library function actually internally does that, right? So yeah, what you say, that was also one concern for me, and then I was hesitant initially. But if you see, like the way he is doing it here, just look for S in this bracket, and then this is my pointer. So when I find this, I just extract two substring. One is the base, and the one is the repeating part. Okay, and then the repeating part, I just keep on adding to the base again for 20 times, and then just pass to this library function, which is the string to double conversion. Okay, the standard library function. And then I return that, and then I do for both of the strings, it works. So
How
when it
you
is,
pick number 20? You
so you
is
can
that
pick 20 or you can pick 16 also. That is what actually I saw there, So some of them are picking only 16, some of them are picking 20, both of them work.
yeah?
Yeah.
So in that case, you would also have to explain to the interviewer why you pick 20, why 1 equals 0.9999.
See, that is one thing, see, because this is a floating point, correct? So the more number of these repetitions you have, so you're closer to the real number, correct? So if you pick 5 or 10 or only two, then sometimes in some corner cases it might give you a wrong input or output, correct? So if you pick, I think it is a 32 or 60, something like that, in decimals, right? You have to have. So that many number of decimals actually which fit in an integer value or a float value or maybe a double value which is 64 bit sometimes, right? So that way you have to fill in that number of digits. So the more you fill, and this your double OER type actually is able to adjust, so then you can pass that much. So
Would
you
that
put the
also
maximum.
depend? It depend on the size of the repeat too, right? You can because if the size of the repeat is large, then you repeat it 20 times versus the size of the repeat like only one, you repeat it 20 times. That
Yeah.
that's different, right?
Yeah. So I think this stod function, it knows that it is going to take a string inside, right? So it might be truncating at a certain uh, point, So for that, it might be doing something internally. Yeah, but your question is right. Sometimes in the repeat, you have like four, four of those which are repeating. And sometimes you have only two, or sometimes you have only one, right? Yeah.
Yeah.
So in that case, how do you take care of that? Yeah, that's important. But I think the more number of repetitions you give, that is the only way I could think of, you know. So the more you give, you are actually closer to the real number, because floating actually is not an exact value. You won't get an exact value at all unless you do the way Shashank was doing, and that is the best way to do, right? Because there you are actually converting it to integer and denominator, and that will give you the right result and exact numbers. So therefore I also was interested in doing that, but then those things came up when I was actually following up. So it said like 52 divided by 990. Initially I thought it was 52 divided by 1000, but then when I really went and looked at the calculation what Shashank is doing, so then actually it's not logically convincing me. Yeah, so that is
Yeah.
one thing, which I thought maybe some
Yeah.
questions. Yeah, what I have, I thought of. Yeah.
But how to prove that 52 by that? I mean, it looks like normal division will show them. No, it won't work, right?
Maybe it is because we have some values after the decimal value, right? They are not, the repeat is not immediately after the decimal value. But in the first case, it was, right, Shashank? In your first
Yeah.
case, it was that. Yeah.
Mm.
So, but still, it is giving you 99. So I think 99 is because it's an approximation again, correct?
Yeah. It- mm. Somewhere we have to stop, right?
So if it would have been 52 divided by 100, right? So it would have been, your output would have been like 0.52, and that is incorrect.
0.5. Yeah. Mm.
Yeah. So in that case, when you want to have a repetition, so I think then it makes sense to say like 52 divided by 99. Correct. So in that case, you are not going to get just 0.52, but you will get something like 50. If you divide 52 by 99, when you really do the division, not the calculator way division, but if you say 520 divided by 99, then you will see the remainder, the remainder will be 52.
In that case, okay.
Yeah.
Yeah.
So if it is a two digit, then it might be 99. If it is three digit, it might be 999, or maybe also 99. Sorry, 990. So that is one thing. I think why it is 990 in the second case is because the repeat is after one digit. You have a non-repeat one, right? Therefore, it is 990. So that is something we'll have to be very, very careful of.
Oh,
You
yeah.
got the point, right? On line 25, you don't have a repeat, right?
Mhm.
Therefore, you are dividing 52 by 99. But on line 26, you have a non-repeat one before
Oh,
52, and that is therefore you say like is 1 by 10. Okay, so that 10 actually you are subtracting from your 999. Okay, maybe then you subtract only 9 in that case, right? Because it is repeating.
in the yeah.
Yeah, so if 1 was repeating, you would have said 10 minus 9, 10 minus 1, and then it would have been 1 by 9.
In that case, yeah. Then 1 by 99 into 9 we'll have to do in that case.
So that is some mathematics going on in that, So why it is 990? So if you look at your way you are converting on line 14, the fractions,
Yeah.
that actually is something which is
We'll have
slightly important.
logic part here. Mm.
So if it no repeating, like there's no parenthesis on 52, so only 0.52, then they're gonna be 52 divided by 100.
Yep.
Yeah. In that case.
But the repeating, then we have to subtract one. Huh?
From 100.
Could you explain that one more time, please, Santos? Why it's 99?
Why it is 99? So okay, so if I say 520, and if I say divide by 99, right? So what I'm getting, if I say I get a value of 5, okay. So then actually, okay, see now I was trying on the calculator here, and actually, so the calculator, the value of 52 divided by 520 divided by 99, it is actually, or maybe 52 divided by 99 is 50.5252, it is endless.
Mm.
So it is
Recurring.
completely repeating. Okay. So if you say, even if I say 52 divided by 98 in that case, then I get a different value, complete different value.
Mm.
So if I exactly divide 52 by 99, it will give me 52 repetitions till the end, and there are many digits, right? So I think if you do it this way, right, 520 and divided by 99, right? So you will get a value 5 points. So if you multiply this by 5, okay, so 99 multiplied by 5, so it will be 495. and if you subtract 495 divided by 520, okay, so you will get 25, correct? So that is the way the division will happen. Now if you have 250, then you again divide that by 99, so you are going to get 2 value, right? And then again you divide that remainder, you will get 5. So 5 and 2 will keep on repeating endlessly.
Mm.
Yeah.
I think these are the basic maths. Maybe we are not really following it very carefully, but yeah, this is the way it is. Or worst case, then we'll have to divide that and show it to him, right? If it is 0.52, if it is repetition, you say 99. But only in the case of for 26 line, then you will have to be slightly careful. Why it is 990? So
There is a proof also for this, like x plus x recurring is equal to.
yeah, so how to get the recurring values, right? Yeah.
Yeah. There is. I don't remember, but I've seen somewhere
Yeah.
some equations they are forming out of that.
So it means like if we do it this way or the way I was converting using a library function, okay, so library function, then we'll have other ways, right? You'll get some different questions, the way Leon was asking, why 20, why 16, all those things, right? So we don't know the internals of the library function. But if we have to go this way, then we'll have to slightly understand this mathematics, correct? And I don't think so it's a big rocket science, something like that. A small thing which we are missing. And if we get there, I did not really spend more time on this. So, but maybe we'll actually, take this in one of our session.
Yeah, this part,
Might
this
just
question.
involve, yeah, we'll understand it carefully, and one of us explain others also. We don't have everyone to do everything like this, right? It should not be me.
Okay. Yeah.
Yeah.
Yeah, let's move to the next one.
Switch to next. Okay, this one. Yeah. So this is like max product of splitted binary tree. So binary tree is given. The root. You have to split into subtrees by removing one edge such that the product of the sum of two subtrees are maximized. Answer will be large, so return the mod of this. So like at this red point, if we are splitting, these two trees are there. One is 11, another is 10, and sum total. If you multiply them, it is 110, which is maximum. Because if you make a cut at this point, 4 will be on this side, and if you sum them up, what it will be 5 2 7 1 8 8 3 11 11 6 17 17 for the 68. So this is the only possibilities where maximum you will get. Same for this, right? This split will give you the max. Yeah, it will have 5k nodes, 50,000 nodes, sorry, and at least 2 nodes. So minimum will be 2 and maximum will be 50,000, and nodes value will die between 1 to 10,000. Okay, yeah. So this again looks like a post order traversal only, right?
Right.
Yeah. Like from you take this root first 4 and then take the entire sum of it, or you can do one thing, you get the total sum of a tree, remove the 4, so remaining sum you will get, right, and then multiply and check that way.
So you are saying post order to get all the values of each and every subtree. For that you are referring as a post order, right?
Yeah, first you do any order in any order to get the entire sum of the values. Even post order, it's fine. After that, you just use post order to get, because once I got the sum of everything, right? Now let's say 4, I want to make a split, so already I have a sum. So in that sum I'll subtract 4, so remaining I got, and I'll multiply that with 4 and just check whether it gives the maximum or not.
Okay.
If it's maximum, I'll take the sum of this total sum I already know, I'll subtract these two, I'll get this, and I'll multiply and check.
Could we look at the constraint? Could it be negative? value?
Negative, it was not there.
Okay.
Yeah, I don't think so. They have said anything about that. Yeah, value is between 1 to 10,000. Yeah, or positive,
Okay.
right? Yeah,
Negative will make it bit more, I think, what do you say?
yeah, but that is very important, right? So
Yeah,
here the constraint was it's good to get it clarified because then it will actually change the whole thing.
exactly. Yeah.
Hmm. So
Yes.
then we'll have to use that monotonic queue part, something like that.
Exactly.
Hmm. That would be very complex. Yeah. But in this case, we could actually still extract the way you are saying a post order.
Hmm.
Okay. So when we are doing a post order to calculate all the first sum of the whole binary, the whole tree, at that time itself, we could get for all other subtrees also.
Yeah. Hmm.
And then actually, when we have all the values, maybe there is an extra space that what you're using. So if you put everything in that something like an array or so, and then after that you actually know that you now you know what value
Total.
is for a particular subtree. Yeah,
Yeah.
and then use the way you are saying. But the way you are doing is also right because then you are not using an extra space, and still you are doing in O of n. Correct.
Uh, no, but I use your approach only. Like, what do you say? I'm taking an extra space first. So first we'll have 4, right? And
Mhm.
then for this we'll have 5. Then 4 plus 5 plus this will be 11, right?
Right.
And now started from here it will be 6, and this will be 6 plus 3 9, and 9 plus 11. What do you say? This one. This will be 21.
Mhm.
So 20. So total sum you got as 21. Now you take each number from here and subtract from 21. So 17 will be on the other side, and here 4. So 4 into 17, 68. Now 4 plus 5, 9. You take and subtract 21.
That's like a pre-sum
Pre-sum kind, not
arrangement.
exactly because we are breaking at some point. Yeah, it's like a pre-sum only kind, you can say.
But yeah, if you can, yeah, depend. If you can construct like a pre-sum, binary index tree, that then we can do range, right?
Mhm.
Range will,
Wow.
but
Okay.
again you have to construct a tree. That yeah.
Yeah, we have to construct it. That
But
extra
then when you
space.
construct a tree and then what you want to do, you want to find a range. Okay.
Range
Yeah,
query.
But is it necessary? In this case, I don't think so, right? You don't want a range.
yeah, not really.
Overrated it becomes here.
So this is slightly simpler. In actually only the extracting part is very important, and
Yeah.
that sometimes it doesn't come so easily also, right? The way you've done, Shashank. Yeah.
Because
Yeah. So that is good. And then you are saying that you know what is the sum of the whole binary tree, and then you use this array to find the most optimum two values, right?
some for that.
Yeah, that
So
makes sense.
two passes in, right? And then big O of n
I
plus
think he's doing a single pass here. He's just collecting everything in the array, and then he's actually traversing the array. But if you consider array as another pass, yeah, then it is two
Yeah.
pass again. Yeah, yeah,
But
makes
then
sense.
the one which I was saying, like I'll do traversal and then subtract every node like that. No, but there are also two passes. Yeah.
mm,
Yeah, so there are also two paths, but what happens when you are going through this recursive way? You are
Yeah.
using a call stack, right? So
Yeah.
that space is slightly sometimes debatable. It might be more than what you use as an array, or maybe even a normal stack, an STL stack, right?
Yeah.
So if you avoid that, it is always good. Yeah, but that is a
So
point for discussions. Yeah.
the
So
same
yeah,
thing
this is
like
one way too. Yeah, okay. Let's go with the way we are done.
so in DFS I'm passing the root, and if there is no root you return 0, and this is the variable that I'm creating sum which will store the sums. And in my answer the root, like it will first explode left, right, and then the root, like post order kind of, right?
Mhm.
root, yeah, and appending it to this, and I'm returning the answer. Once I got the answer array, now I'll do this part. For every x in my sum, I'll just x minus total minus x, the complement. Because only one split we have to make, two parts we have to divide, right? So whichever of them is maximum in that product, just take the modulus of it.
Yeah, makes sense.
You could, avoid the array, right? You could avoid the array. You only need to get the sum, and then like
Then
Santos
again,
say, and you do the post order traversal,
Right,
and
right.
yeah, that case array we can avoid.
Yeah, so you avoid that, okay, and then again do a post order traversal to find the minimum, right? Yeah,
Maximum.
yeah. Oh, sorry, the maximum.
Right.
Yeah. So actually, these are the solutions part. They are in the solutions also. So yeah, I have actually just copied it from the solutions. Okay, I'll just quickly run through. So that is almost the same what.
Or you can use iterative, but that will be,
Yeah, but then it will be an additional overhead, right?
yeah,
Yeah.
that's shown.
So this is the one. So this is your function signature, right? Max product. So first you get your total sum using post order. You don't use any array. So this is that post order. Okay, so in this post order, and this is my total sum. So the total sum is here. So I just go in the post order, left, right, and then the sum of the ND value, the root value, left and right, and then sum. You keep on returning. So therefore, your total sum will be the sum of everything. And then you again go for another function called max product. It is actually doing another post order traversal. In that case, do the similar things, like you get the left and right side, and this is actually the sum of all, even the root value, along with the right and left, and that is what you will be returning. Okay, at the same time, this will be a global variable, and then you see if it is a take that maximum the way you are describing,
Yeah.
d sum multiplied by total sum minus d sum, right? So it is exactly the same, but just avoiding the array, right?
Yeah.
Yeah,
Space optimizing.
right. So the only other part is, yeah, you have to still do a mod 7. So the other part is I'm using a long instead of integer. So there was one more solution in the solutions, and it said, like, in case if you don't want to use a long, because some of the languages or some of the platforms might restrict you to only use 32-bit, right? So then how do you do that? Because anyway you are using mod 7, and your mod 7 you are still restricting to 32 bits, right?
Yeah.
So then how to avoid using long ones, because sometimes the data types are not present in some of the platform. So what they did, there was a very slight small different thing, in the sense you first do the post order, get all your value. Okay, so when you get all your value, so this is your post order, very simple. And then you also push that in your
So
result.
result there. Yeah.
Yeah, so everything is integer. If you look at here, just push into the result, but then you use a modular multiplication. So this is the function what they are using, and what that function does is, before going there, so this is what you are doing, right, Shashank? When you
Yeah.
took from
Totally.
that array, and then every time, but in this case what I'm trying to do here is trying to find the closest distance, means the number which will have a very small difference between, and so like it is 10 and 11, right? Okay, so 10 and 11 will are the ones which are having the smallest distance. And how do you find that? You take the total, and each and every um, subtree's sum, you multiply by 2 and subtract from the total, and you see this distance actually, and keep the minimum distance. So whatever is the minimum distance you are actually maintaining here, and as soon as you find the most minimum, so that particular value you store. Okay.
Mm.
So that particular value, you say it is nearest to the half value. So maybe it might be 10 or 11. So because if you look at this example, so the maximum value will be always when they both the numbers 11 or 10, they are very close to each other. Then only you will get the maximum value, right?
So
Anytime. So the one which are very closer to each other and they are at the midpoint, right?
midpoint, yeah.
So the numbers are which are the almost closer to the midpoint, those will always give the maximum number. So that is what he's trying to do, and then he passes that as an input to this modular multiplication. And now you know that you have one number, so the other number you just subtract from the total, you will get the other number. And this modern modular multiplication is a very simple thing what we do, like when we want to multiply a number. So what we do is like, if this is our current number, which we have actually set to A, okay, and
Yeah.
then this is the B part actually, then we run in a while loop till the B doesn't become 0. So the way we do is we extract the last bit of the B, and if that bit, okay, if it is 1, so then only you actually add your current value to your product. So actually you are getting a product value inside the year, right? So you keep on adding the current, okay? And this modulus part is a standard one. But when you do, every time you will have to shift the current also,
Left
correct?
shift. Mm.
So this is a normal mathematics, right? So the normal multiplication, what we do. So if we had something like 52, okay, 52 1 multiplied by 19, right? So first what we do is, when we want to multiply by 9, so we multiply this, whatever the values we get, like maybe there are 4 values here. But the next time when we want to multiply by 1, so we'll have to shift this value by 1 digit, right?
Okay. Yeah.
So that is what actually he's doing here, but it is a bitwise division, right? So whenever you multiply this, so your 5 to 1 will come over here. So it is 1 digit shifted to
Shift
the
towards
left
left.
side, right?
Yeah.
So that is what he does for the current also, right? So
Yeah.
that is what happens here.
We have multiplied two strings problem. There we use this modular multiplication.
Yeah.
Yeah.
So it is like bitwise multiplication, but the why we are avoiding a long in this case, because we are always adding, so we don't have to multiply, and therefore if we multiply integer with this, so the intermediate values will be greater, right? So you'll have to store somewhere
Yeah.
when you want to do a comparison, the way you do comparison here. So the previous values, right, the previous ones where when we are comparing like these ones, so if the numbers are very big, so that is for that reason you have to use a long. So these integer values are used when you have two big numbers which are closer to almost going to overflow this integer 32, and when you divide two such numbers, right, so
Yeah.
that value will be bigger, but your answer is not really supposed to be bigger in that case, right? So to avoid that, actually they are using this trick. And out of the whole thing, this modular multiplication was the one which was slightly different. So this is one way of multiplying in case if we are supposed to multiply. Oh, sorry. If we are supposed to multiply only in a 32 bit, so don't
Yeah.
exceed the bits.
That's a good part. Like you brought it.
Yeah, that
Because
was in the
earlier
solutions actually. Mhm.
I used to do integer multiplication where I used to create a result array of multiplication of A and B will be the length of A plus length of B plus 1, and
Mhm.
then go at that particular place and multiply and put the value. But this is a very optimized approach to do multiplying two numbers, modular multiplication.
Yeah.
Yeah.
Yeah, but I think this is very specific to this problem because you find the nearest to half first, because that is very important. because you're almost close to what you want, right? And then
Yeah.
you know the two numbers, and then now the only thing is you have to multiply both of them.
In that
So
case.
instead of using the normal multiplication, which will consume more bits than 32, so then you can do it this way. Yeah, but I don't think so it will be a part of an interview, right? I also would never remember this.
Yeah, it's a little bit,
Yeah,
what do you
but
say?
worst case, if someone tries to push, then okay, then we can always say there is something like this. We could, because it looks like a normal bit multiplication, right? So whenever
Yeah.
we want to multiply any bit, so if the last bit value is 1, so you copy the whole the whatever your multiplicand or multiplication factor, right? So whichever the one which you are adding, so you'll copy the whole as is. But if you are moving in the bits further, if it is 0 bit, you don't want to copy. But if it is 1 bit, but you still have to push the whole the the factor which was a in this case, right? So you'll have to
Yeah.
keep on pushing to the left side always. Yeah.
Yeah, yeah, that's true. So, yeah, we can move to next. Yeah. So, time complexity will be of n only because two passes we are making, right?
Right, right.
And
It is almost the same for all the solutions what were presented there. Yeah.
yeah. So next is like sum of square of numbers, and we are given a non-negative integer, that means 0 and positive. Decide whether there are two integers a and b such that a square plus b square that's equal to c. Okay, this is like yesterday's problem only, right? If you can break this number into a perfect square kind of thing, right?
Oh,
That,
we had a problem yesterday. I don't think so. Maybe before
no,
that.
that grid problem what Uday was trying to come up with, uh, m cross n multiplication should be equal to the sum of some perfect square, something like that. Like that grid we had right yesterday, in
Yeah.
which tiles we were fitting the tiles.
Oh, the tiling one, right? Oh, yeah.
Yeah,
For
yeah, yeah,
the tile, the way Raj, he referred one video, right?
yeah, yeah, yeah.
Okay, so that is also one way of doing. Okay, yeah. Uday's way was also good. Yeah. So yeah. So sorry, you got you were explaining something.
Yeah. No, I'm saying that Uday was also trying this only. The product of the rectangle, he was trying to break into sum of some perfect squares. So I'm saying somewhat this problem is similar to that. Number 5 is given. You have to check whether you can break that number into sum of perfect square.
Mm-hmm. Well, the way Uday was describing yesterday, if I remember it, he was saying, you
Yeah.
start with some squares, like you know that the maximum square size will always be 13, right?
Yeah.
So from there, you start with 13 and you try to find how much 13 square will fit in, and you subtract that, and whatever is remaining, you recursively do for from 13 to 1. Okay. So now when
Okay.
you are done with the first pass, where you started with 13, you save the result, and then next time you go for start with 12, and then you
Mhm.
find. Then you keep on decreasing that value till you come to 1. Okay. So then whichever is the minimum so far, the way I think he was coming up, you should get that value, right?
Yeah, in that case, yeah.
So maybe that is also one way of doing it. But I was trying that maybe when he is on some session we can talk about that. But the other thing is when the way Raj, he pointed out to some video which was about the skyline problem, right?
Yeah.
Yeah. So that problem is really good problem, because that has a pattern, correct? And
Yeah.
that pattern, so Uday's will also work, but I'm not sure whether there is any implementation proof for it yet. Okay. So maybe he will work on it, or maybe we all also can work on that and see if we can find that value,
Yeah.
find that approach. But Raj problem is a proven one because the skyline problem pattern can be used for many other problems. Okay, I'm not saying it will be relevant for like hundreds of problems, but at least there is some that pattern can be matched with at least 4 to 5 such problems in Leetcode. So that will be a very important one to study.
Yeah, we have skyline problem also
Right,
separately.
right.
Yeah.
Yeah.
Using, but we use heap in that case, max heap.
Yeah, so whatever you can, that should be fine. And there are different ways to do it and different tricks also. But I think we
Yeah.
should also discuss about that sometime. So maybe I'll put that in our notes in the session what we have on Tuesday and Friday, right?
Yeah, yeah, definitely.
That session, yeah. Maybe bring that. Yeah, okay. I'm sorry to go
Oh,
away
you can
from
share
this problem.
that YouTube channel. I lost it because chat in the lead code, the one which Raj shared.
Uh,
I missed it. Yeah.
okay, yeah, I can point out. Yeah, I can share that also. Sure, I'll do that. Okay, so
So
this problem is slightly different, right? Okay.
little bit, yeah. So here just we have to find whether we can break the entire C into sum of product of perfect squares, right?
Mm-hmm.
Sum of perfect squares.
Right.
Yeah. So
So
one,
how do we do like a brute force now in this case? That brute force will surely work, right? The way it is a square plus b square.
yeah, 1 to 5 you
Yeah.
run a for loop here. And then
Not even 1 to 5. You can actually start from 1, and if that 1 you keep on going till root 5. Correct. So till
oh,
root 5.
okay.
So you start from 1 to root 5, and in that case, because root 5 multiplied by root 5 will give you 5, right?
Yeah.
So that is the max you can go. So you can find A in that case, and then you can also calculate B similarly, just by subtracting that value and see if the square matches with your
Should we
C, right?
start from zero?
I'm sorry, Nick.
Should we start from zero, not from one, but from zero?
Oh yeah, you are right. Yeah, from 0, correct.
0.
You'll have to start from 0 because yeah, if it is 4 in the case of C, then that itself is 1 square, right? So and then 4 will be 2 square plus 0 square. So then it is true. Yeah, you're right.
Or you take a number, square it, and subtract from C, and whatever you number you got, you take the perfect square of it.
Oh
If
yeah,
it is
you'll have to find out a square for it also. Mhm.
Uh,
if
can
it
we
is
use the formula like a square plus b square minus 2ab, something like that? C is equal to 2ab and c is equal to a square plus b square.
yeah,
Uh,
but he's saying
so
B square. I mean, are you saying this square only, right?
Yeah, like a minus 2 a minus b whole square.
mhm. Okay,
Oh, so
so this way
you'll bring this side, these
minus
things, right?
2ab.
A square plus B square, and by 2 you do, and your AB is equal to C. Is it?
Like
Mm.
yeah, something like that. Like or we can, like I'm saying, like only a minus b whole square. Like we will add minus 2ab on both sides.
Okay, so this will be terminated, and this will be minus 2.
Okay.
But
Yeah,
what
but
do you
you
get
still
equal to?
have to go for two numbers, right? So two distinct numbers.
Yeah.
Yeah, so I was also thinking if we can find a formula, just fill in that formula from 0 to root 5, and then you should get the other value, right? Yeah. Hmm. Yeah, that is one way of looking at it, as well as it can be solved in very constant time, right? Hmm.
Can we use binary search for this?
Yeah,
Yeah,
binary
that's a
search
good
also
one.
would be one way. Yeah,
Yeah.
yeah, that is for sure one way.
So there is this two-pointer approach where it goes from left and right. If while left is less than equal to right, So right always calculates this, because right at first right would always be the c, but it does the square root and converts that to int, and then we find the sum. But I didn't really quite get that 2-pointer solution. Did any of you guys get it or have seen it?
It's like a
Uh,
search only, I think. What is it?
2-pointer, right? Yeah, I think
So
so. That's not a very
one at right you keep, right? One at left. Is it like this?
Yeah. So just like that. Now on the right, what we do is we find the square root of 5 first. It's going to be 2 point something, but if we convert that to int, it'll be 2. So
Yeah.
then we'll find the sum. Sum will be left times left plus a right time right. And when sum is equals to c, that's where we're going to return a 2. If sum is greater than c, then right will go down, minus minus. If sum is less than c, then left will go up, plus plus.
yeah. That should work, right?
It works, but I'm trying to understand why it worked. Yeah.
Okay. So because so if you, the first value what you take, maybe the right or left, whatever it is, you will actually do something like a square root of c, something like that, right, to get that value. And if that is actually itself satisfying your perfect square, you return. And then you start from the other value, like in this case, if you see the right value is root of 5 and your left value is 1. Okay, so if you just multiply both of them, squaring both of them, and if you get the perfect c solution, you return true, right? But if you are getting a value which is greater, so you know that your this value, this the left
And
value has to be.
increased.
Oh no, if you are getting greater, then you'll have to reduce your right?
Yeah. Greater, we have to reduce the right pointer.
Right, yeah. So then
It,
if you are doing it one by one,
Hmm.
so then you should get that value. Unless and
yeah.
until you are not over crossing both the pointers. If you are
Pointer.
crossing the pointer, it means it's not possible.
Mm.
Should
It's
work,
like
right? Because the normal way. Sorry, go ahead, Shashank. Yeah.
no, no. I'm saying it's like a sum of two numbers. You are checking whether it's equal to target or not.
Exactly. Yeah.
Right,
Same
right.
idea.
Yeah,
Same
Yeah.
thinking. Yeah.
that's a perfect way to put it. Yeah.
Yeah, just a couple of words from my side. And as I understand, we should start from not from C, but from square of a C, because we can have overflow. Yeah, if we start from C, because if our right will equal to C, when we C multiply to C, we can have a overflow. Yeah.
No, C is already the square of your square of the numbers, right?
Yeah.
So why
Yeah.
you?
Yeah, I'm asking about ranges. Which ranges should we start from 0, and what about second range? As I understand, it could be just square of C, not exactly C, but square of C, because in case of C we can have buffer overflow, number overflow an issue. Yeah.
Right. So you're right. It's taking not necessarily square, but it's taking the square root of c. That's what it's
Yeah.
taking.
Yeah. Yeah.
Correct. Yeah.
Hmm.
So you start from there, and then actually, so he's also saying instead of left you have 1, you can make it 0 also, right? So
Yeah. The left actually starts at 0 because it says non-negative integer. So.
Okay.
okay, yeah.
Mhm.
But then it is straightforward. Only the thing is how to come up with the right value first, And now I think Nick, the way Nick says, and we all agree, like if it is square root of that c, then it makes a perfect sense, right? Then that is what we are starting from,
Mhm.
and then we keep on moving both the pointers closer to each other. So we should get a value. If we don't get, then it is fine. We return false.
So then,
Yeah.
if you take root C, then left and right values what you are taking, you have to take the root of that also, right? And then add.
No, no,
No,
no. The
what
left
if
and right, you're just getting the. I think the root. You are only taking the root of right. Left, you're just taking the value like by itself. Yeah.
yeah?
So then
So the
how
left
will you?
value will start from 0.
Mm-hmm.
So you take only the square root of c, and that will be your right value.
Mm-hmm.
Okay.
Yeah. I think so. That should be, yeah. Okay, he has shared some. Okay. Do you want to copy that?
Yeah,
Okay.
sure. Let me copy it.
He has also shown some example there. Yeah, that makes sense. Or do you want to share, Nick, your screen?
Yeah, if Nick wants to share. Do you want to share, Nick? I think is.
Maybe he is busy. Yeah. Okay. Okay.
Yeah, I can. I did it too. I'll just share mine.
Okay.
Okay,
Yeah. No
okay.
problem. You can share it.
Go
Yeah. Right. Same approach, right? Um, so left starts at 0, right starts at let's say 5, left is less than or equal to 0. Same, I just didn't use the else class, but it calculates the sum first. When sum is exactly C, that's when we know we have it satisfies this condition A squares plus B squared. We have A and B that satisfies that condition A squares plus B squared equals to C. Otherwise, you just go right and left. At the end, if you couldn't find it, it returns false.
Mm-hmm. Yeah.
My
Yeah.
why right you are taking as root of C? That I'm not getting.
So the way I don't know, I'm trying I tried to hand trace it last night too. So if we just look at 0 and 5, right? So let me
So Sushant, in that
Yeah.
you have that equation a square plus b square is equal to c. So let's say a is 0, then what will be your b? And you know the c.
Root C. Yeah.
That's
Yeah.
why.
Okay. But if A is 1, then in that case.
No, that's why you starting with that a is 0, and then you will exploring all these values.
yeah.
Okay, yeah. Yeah.
So
Then
left and right, when we do left and right, this comes down to 2 on this first iteration, right? So it'll be sum would be 0 square plus 2 square, 4. And some right now we're assuming our C is 5. This is our C for now. Well, let's say this is our C for now. Okay, 4. Um, 0, so some 0 square plus 2
2
square,
square. Yeah.
4,
4.
4. Mm,
So your five's root
Square root of
no,
C is
5
the
should
upper
be,
limit.
will still be 2, right? Yeah. Because you are
yeah,
taking an integer value. That should be
yeah,
fine.
yeah. Yes, this is 5. Let's do the example one. See, so 0, this will be 4.
Mm-hmm.
Now, if sum is less than C, so now we have to increase our left. So my left will go here,
Yeah.
and then it goes back to the loop, and then let's see,
So
then
you will get the value 1 plus 4.
yeah, then I'll get 1 plus 2 square plus 1, then I'll get 5, and that's when I know this is
Yeah.
what happens in example 1. So basically the time complexity is O of not
Root N.
necessarily n, but the O of square root of C, because depending on the square root of C, that's how we know how many loops we're doing on this while loop.
Yeah.
Yeah.
Slightly, but still it will always be said as O of n, right? Yeah.
Yeah.
You can say, hey, you have a lot of optimizations there. Yeah. Yeah. Makes sense. So this is a good approach.
Or here only, I mean, binary search you can use, right? Mid you have calculated left plus right.
Yeah.
And
I think Ankit was saying that, right?
saying, yeah, yeah.
Yeah, that is one approach of binary search also. That also makes sense, right? So in that
Yeah.
case, what do you think? If it is a binary search, will it be log n?
Log of, yeah, it looks like that. Log of 5. Yeah, log of n.
Okay.
No,
So, but
I
this
think in
also
binary
will be
search
all
it
of
will be,
log of n, right? The way shuffle is showing.
for binary search, I think it will be log root C
Of the
log
square
C.
root of c.
Square root of c. Okay.
Yeah, I mean, root will become constant if you take base 2. Half power will go down, right?
Okay.
So this one it will be log factor.
Okay.
Yeah.
That's interesting. Yeah. Yeah.
Yeah. So,
I'll stop my share.
Yeah, no problem. Yeah, thank you. Yeah.
Mhm.
And one, like, it's just simple. I mean, this is more time taking what I did. I'm just taking a set, and your count is like square root of C, and that is like till that extent will go, right? Because our
Mhm.
first index is 0. If A is 0, B will be root of C.
Correct.
So you just go and keep on adding your squares to this set,
Mhm.
and for every number in the square, if the complement of it is present there, that means you got both the pairs.
That's interesting.
Yeah, but extra space, the square is there. Otherwise false.
Mm-hmm. Yeah, I never thought of this. Yeah, this is a good one too.
Number and its complement, but it's taking space. But shuffles was, I mean, totally, what do you say, space optimized.
Yeah, but the time of complexity will be okay, almost same for both of them, right? Yeah. Hmm.
These will also go root C.
Yeah.
Because you're also counting in the root.
Yeah.
Okay. So you let's discuss the binary one also. Yeah, Ankit, do you have something to discuss?
Actually,
Binary
I
search?
don't have it implemented one. I was just giving it a thought.
Oh, okay. So in that case, I think we can still do binary search also, right?
Yeah. I mean, I implemented using that two pointer approach only, but for the
Uh-huh.
binary search, I was thinking, like if we have the C value and if we choose A, then we can
Mhm.
get the B out of it and then we can search it in the array if we are able to find the B.
Right, right, right.
But I don't have it implemented right now.
Okay, okay, no problem.
Some of them are using this formats theorem. Like we have this. That is, I'll
Which
show
one?
you that. I'm showing this one. This is the theorem, right? I mean, we can always express a natural number as a sum of two squares, if and only if the each prime factor, uh, if each prime factor, that's 3 modulo 4, occurs to an even power in the numbers prime factorization. It's like mathematically you have to go right. This is what Fermat's theorem is, right? 3 mod 4 will be equal to the even power in when you do the, I mean, when you do the prime factorization of a number, right? And if you
Uh-huh.
take 3 mod theorem, that is an even power of it, then uh,
Okay.
then it can be expressed as the sum of two natural, what is a sum of two squares.
Hmm.
Yeah, this is that equation. P mod 4 not equal to 3.
And one thing what was discussed in the solution that, if you add all these odd numbers, you'll
Okay.
always get a perfect square. You know that, right?
Yeah, I saw that. That was
Yeah.
interesting.
Yeah, that was very good. But it was stealing actually. Therefore, it was not getting more inputs. Like if you have number one, right? And if you, the second will be three, right? So
Yeah.
if then will be 5, 7, 9, 11. So if you see, if you add 3, 1 will be 4, right? So 4 plus 5 will be 9. 9 plus 7 will be 16. 16 plus 9 will be 25. 25
Oh,
plus 11 will be 36. And
36. Yeah.
36 plus 13 will be
49.
49, right? And then you have 15. So 36 plus 49
54.
plus 15, 64, right?
Yeah.
So and so forth, So you'll always get that number. You'll always get a perfect square.
Yeah, it's interesting. I today.
Yeah, I also was not knowing that. But then there is one solution. What he is saying, you actually look for only a first, and then go all the way to square root of a till you hit on c. But then when you find an a, then how to find a b? So the next b, you take that b and try to see if you can find it as a square in this way. Keep on adding the odd numbers, and then if it is equal to, because that if you find any number when you're adding the odd numbers, so
It
if
will
you find
perfect.
the b in this number range, then you are a perfect square. Or else if you just overcross the b number, if it is b number was between 25 and 36, then it means that it's not an perfect sum, perfect square sum. So that is what they were using, but it hits on a TLE because of this long addition, right?
Yeah, but it's a good, very good, what do you say? I mean, number theory knowledge, like sum
Yeah,
of
so
all.
it might be useful somewhere.
What about even? It won't, right?
No, even you don't get it. It's only for the odd.
So you were saying something in the solution. What was that?
This was in the solution.
Oh, this was only.
These are all, yeah, these are all part of solutions. Yeah.
It's a very good one, but
Yeah. Yeah. So
yeah.
that was good.
Good.
Let
Today.
me stop the recording.